All right, it's time for a totally unrehearsed pop-up lesson here. When we did the last problem, the 2004 problem from Heck, uh, we talked about using the parallel axis theorem to find the moment of inertia. And I said there was another way to do it. And I'd like to talk about that other way because this is how you're going to have to attack the problem from hell. So let's just remind you that we have a bar of mass m and length L. It is uniform. And we are going to be pivoting it here at a distance L over 3 away from the end. So if you're trying to find the moment of inertia of something and you don't even know what the moment of inertia around the center of mass is, you really have to go with the original definition of the moment of inertia, which is the integral r squared dm. And I said that that's a very unfortunate integral because it's easy enough to figure out the limits, 0 to the total mass of the object, but it's really difficult to figure out how the mass is related to r. So it's really good to use the idea of density. And in this case, we're going to go with linear density. Now, linear density in this case is two things. First of all, it is the total mass of the object, and I'm using the capital M here to help me out, divided by the total length of the object. That is what uniform density is. But it's also any smaller mass divided by some smaller distance, L or X, we could call it, or even an incremental mass divided by an incremental distance. So this is how we're going to achieve our substitution. And I usually go back and use the letter lambda, and then I substitute in m over L for it later. Maybe this time I won't. Maybe this time I will say that an incremental bit of mass over an incremental distance along the x direction is equal to the total mass of the object. I'll try to make that look like a capital M as much as I can without the feet, over the total length. And that means that we can substitute dm with capital M over L dx. And that's how we're going to get rid of this in the integral. Okay, two things that are going on here. First of all, r is a generic variable inside this definition, and we are specifically looking at the x direction. So I'm going to replace this with an x squared. And second of all, we're going to have to think about the limits. So let's just go ahead and rewrite this integral as the integral of x squared. Oh, I did the feet again. M over L dx. Now, this is where cleverness comes in. I really want this thing to be easy to do. And sometimes that means choosing a coordinate system where this is 0, and we're going to have positive numbers to the right, and we're going to have negative numbers to the left. That means that my limits of integration are going to go from minus L over 3 to positive 2L over 3. Now, I know I've made this integral look a little confused. I've written it too small, but we're going to fix this up right away. Let's make some space. First of all, we can pull out the M over L, and then we have an integral of x squared dx going from minus L over 3 to 2L over 3. That's a really easy integral to do because what we do is we increase the power by 1, and we put the new power underneath, so x cubed over 3. Basic polynomial integration from minus L over 3 to 2L over 3. Okay, going down another line, M over L, M over 3L, why not? And now we're going to have upper limit 2L over 3 cubed minus lower limit minus L over 3 cubed. Okay, we've got M over 3L. Now, 2 cubed is 8, L cubed, 3 cubed is 9, 27, right? Okay, and then that's minus, okay. Okay, short interruption there. So we are trying to cube this thing. Now minus, okay, so minus L cubed is still minus L cubed. And 3 cubed is 27. Okay, wow. Okay, minus minus is a plus. So now it looks like we have 3L. Grand total of 8 minus a minus 1 is 9 L cubed over 27. Okay, this is cool. 9 and 27 is a third. And this L and that L are going to do some cancellation of sorts. So we're going to have, where was I? 27, 1/3 and another third. So that's going to bind up with 1/9 mL squared, which is exactly what we got before. Now, this is harder than the parallel axis theorem, but we had to know the moment of inertia around the center of mass to use the parallel axis theorem. This will also work for a non-uniform bar, which is what we get when we do the physical pendulum from hell. So just thought I'd throw this out there. It might help you. I did release to you the physical pendulum from hell. We will do it as an in-class exercise, but man, it'd be great if you could take a look at it before we did. Thank you.